LUDO, low latency understanding of deformable objects using point cloud occupancy functions. First, we want to show you what LUDO does. Given a deformable object, LUDO provides 3D structural information about the deforming object and its internal structures. In this example, we have a small organ-like structure with 3 embedded spherical ROIs, or regions of interest. As this object is deformed, LUDO provides structural information of the organ, seen in the top in pink, and the 3 embedded ROIs, seen at the bottom in the 3 different colors. The observation point cloud from the depth sensor is also overlaid and is visible in the bottom. On the right, you can see the video captured by the depth sensor while it was recording. As just shown, the main motivation is to provide 3D structural data of deformable objects. We focus on single view observations. This is a practical consideration, as objects can usually only be observed from limited angles. We want to obtain structural information at an interactive speed to allow automation and robotic interactions with the deforming objects. Finally, receiving structural data alone is not enough if there is no way to tell if the structural information is of good quality. Therefore, we include uncertainty and explainability to our LUDO estimates. LUDO itself is trained in simulation. We assume the deformable object is known prior. In a medical context, they can usually be obtained from a preoperative CT scan. Similarly, in industrial applications, either an industrial CT or a CAD model of the object of interest is often available. This prior model is deformed in simulation to create deformation states. For supervision, LUDO watches these deformations and learns to infer the 3D shape of the objects in their deformed state. At its core, LUDO consists of an occupancy network with a point cloud encoder. Therefore, conditioned on a point cloud, LUDO learns to label Cartesian points with inside and outside labels. Sets of points labeled as inside represent our object of interest. During inference, LUDO is conditioned on the observation from a depth sensor and queried using randomly sampled points. The output being the labeled query points, in our application usually 40,000 points. The time needed to obtain such a labeled point cloud, given the observation, is less than 30 milliseconds on consumer hardware. The output point cloud can then be used for trajectory planning and robotic tasks, for example the puncturing of the embedded regions of interests, seen in blue, gray and green in the second image from the left. Due to the low inference time, LUDO can be used to obtain live structural information of deforming objects. For the video on the right, we use a low-cost depth sensor that can provide depth information at up to 60 frames per second. The camera is attached to a laptop, which streams the observation point cloud to a workstation, which performs the LUDO inference. The resulting labeled point cloud is sent back to the laptop for displaying. All of this happens on a Wi-Fi network. Still, you can see the responsiveness of our output point cloud to the real environment. We can loosely divide the output point cloud into 2 parts, which is the inside points and the outside points. For the visualization, we only show the inside points, as the outside points would obscure the view. As stated previously, we integrate methods to compute uncertainty and explainability for deformable object understanding. We provide both a local and aggregated uncertainty. Therefore, we can determine what parts of the deformable object LUDO is very certain about, and if the inferred structural information is reliable as a whole. In the top left, we see the local uncertainty values, which are high around the surface of the object. This is because it is difficult for the occupancy network to decide if a point close to the boundary belongs to the inside or the outside of the object. If the input data is disturbed, for example by adding noise, you can see that the decision boundary spreads out. By aggregating all local uncertainties, we also obtain a single scalar value that indicates the overall uncertainty. In the bottom left, we show 3 observations of the cylinder that result in an aggregated uncertainty that falls outside 1 standard deviation from the mean over the training dataset. A is an observation of the cylinder that is bent into an upside-down U-shape. The observation results in ambiguities regarding the labels of the outer internal ROIs. Said differently, it isn't clear where the top and the bottom is. B is an observation of the cylinder with large missing regions caused by self-occlusion. C is an observation where only the top part of the cylinder is visible. The bottom half is not visible at all and cannot be reasoned about. For explainability, we use a masking-based approach that removes parts of the observation and evaluates how much that affects LUDO's labeling. On the right, you can see one example explainability point cloud for each object. The red regions are areas that have the biggest impact on estimating the deformation of each object. Highlighted areas include the bump on top of the organ, which is an important feature to locate the underlying region of interest, the starting and end points of the cylinder, and the corners from which the slab is deformed. we compare LUDO to volume to surface CNN, or V2S for short, a popular data-driven deformable object registration method. The task is to localize the spherical regions of interest inside of the deformable objects. The centroid error is shown in the table on the right in centimeters, so that is the error between the estimated and the true position of the region of interest. For the comparison, we consider multiple configurations of V2S. We always provide V2S with an optimal initial alignment, as V2S struggles to find this initial alignment itself. Both models are trained for 100 epochs, at which point the accuracy of V2S is saturated. Most importantly, we outperform V2S given the optimal alignment, full surface observations, so not just single view observations, trained on the same data as LUDO. LUDO asterisk shows that LUDO continues to improve noticeably if trained further, in this case for another 500 epochs. We want to mention that due to LUDO's more efficient data representation, one epoch takes orders of magnitude less time to train than one epoch for V2S. Finally, we evaluate LUDO using a robotic setup. We consider the task of puncturing the spherical regions of interest inside the three deformable objects. For this, we use our calibrated robotic arm and a high-quality structured light-based depth sensor. The overall success rate of hitting the regions of interest across 90 total punctures was 98.9%.